Hello, boys and girls. Today we're going to solve some of the past papers that are also related to the thermal physics topic. Now, let's start with this question. Just to remind you, the index up here in each page, it represents the year the past paper was taken from. So this is from May, June. It's paper 4, variant 1 for the year 2016. Okay. So, state what happens to the molecules of a gas in a sealed container, sealed which means closed, when the temperature of the gas is increased. So here, if we increase the temperature, the molecules will have more kinetic energy, so they will move faster. They will hit the walls of the container more frequently, more collisions will happen, and since there are more collisions, so we will have a change in momentum, which will give us a greater force. So here we only have to choose 1 point for this question. Now, a quantity of gas is contained in a sealed container of fixed volume. The temperature of the gas is also increased. State, in terms of the molecules, 2 reasons why the pressure increases. It's the same as the first one. So you have to choose 2 points other than the one you've chosen here. So here, for example, if you choose point 1, you'll have to write 2 and 3 here. Okay, so it's basically when you heat up a gas, when you increase the temperature, the molecules will have more kinetic energy, so they will move faster. They will hit the walls of the container more frequently. So when we have more collisions, we will have a change in momentum. This change in momentum is going to give us a greater force, since the force it is the rate of change of momentum. Now let's go to C. A helium-filled weather balloon is held at ground level. The volume of the balloon is 4,800 meter cubed. The pressure of the helium is 98 kilopascals. The balloon is released and rises to a height where the volume of the balloon is 7,200 meter cube. Now calculate the new pressure of the helium. Assume that the temperature stays constant. Now here, since we're assuming that the temperature is constant and we want a new pressure, so we have a volume and a new volume, and we have a pressure and a new pressure, so we will use this formula right here, which is P1 V1 equals P2 V2. So P1, which is 98 kilopascals, so here I put, instead of the kilos, I put this 3 zeros, times V1, which is the initial volume, the volume before the release of the balloon, equals P2, which is the new pressure that I want to find, multiplied by V2, which is 7,200 meter cubed. And here, in order to find P2, we divide both sides by 7,200, and so the answer will be almost 65 kilopascal, of course, using significant figures. Now suggest why it may be necessary to release helium from the balloon as it rises even higher. So why do we have to remove some of the helium from the balloon? Because we don't want the balloon to burst. So if you have more volume, the helium will expand more, so the balloon will burst. So that's why we have to release some of the helium in order to decrease the volume, so it won't increase so much and burst the balloon. Okay, so this question is one of the specimen. It's from one of the specimen papers. It's paper 4 for the year 2016. So figure 5.1 shows a gas contained in a cylinder enclosed by a piston. At first, the length of the cylinder containing the gas is 100 centimeters. The pressure of the gas shown by the pressure gauge is 300 kilopascals. The area of cross-section of the cylinder is 0.12 meters squared. So describe the motion of the molecules of the gas. So generally, the molecules of the gas, they move randomly. They have high speeds. and they collide with each other and also with the walls of the container. You are welcome to choose any one of these points. Now use the idea of momentum, and this is important when the question says that you have to use an idea or you have to write it in terms of something. You have to use that idea to explain how the molecules exert a force on the walls of the container, of the cylinder. So we said that when we have collisions of the molecules with the walls of the container, they cause a change in momentum of these molecules, which this change in momentum, it will result in the need to have a force. Now, of course, since the force, it is basically the rate of change of momentum. So we will need a force in order to change the momentum. So that's how we get a force. So the collisions, they create a change in momentum, and the force, it is basically the rate of change in momentum, and that's why we will eventually have a force exerted on the walls of the cylinder. Okay. Now, the piston is moved so that the new length of cylinder occupied by the gas is 40 centimeters. So it was at first, it was 100, right? And now it became 40. So we pushed it to the right. Okay, we made the volume decrease. We made it less. So the temperature of the gas is unchanged. Now calculate the new pressure. So we also use this formula, P1V1 equals P2V2. Now P1, it is the pressure at the beginning, which is 300, right? 300 kilopascal. Now the new pressure, which is what I want to find. Now the idea here is in the volume. Now as you can see, we are giving the area of the cross section, which is constant in both cases. Even if after you push the piston to the right and made this 100 centimeters 40, the cross section area, it's still the same. So you have to remember here a really simple concept that you've taken or heard of it in math, which is that the volume, it is the area multiplied by the length, which is in this case that we changed from 100 to 40. So to calculate V1, we have to multiply 100 centimeters multiplied by 0.12, which is the area. Now, why here? Why did I divide by 100? Because I want to convert it from centimeters to meters, because the area is given in meters squared, so the length also has to be in meters. Equals P2, which is the pressure I want to find, multiplied by the volume, which is the area, multiplied by the length, which is 40 centimeters, and we have to convert this centimeters to meters, so we divide by 100. So doing the math here, multiplying the numbers, so here in order to get P2, I have to divide both sides by 0.048. So eventually the new pressure will be 750 kilopascals. Of course here, why did I put it in kilopascals? Because straight from the beginning, I just left the 300 kilopascals as 300. I didn't add the 3 zeros. Now explain in terms of the behavior of the molecules, why the pressure has changed. Now why did the pressure change when we, as you can see, it was 300 and it became 750. So when we make the volume less, more collisions are frequent with the walls of the container per second, which is the force. So a greater force, it will be per unit area. So it's just because that when we pushed the piston, we decreased the volume, so more collisions are frequent to happen, and it will give us a greater force. Okay, now let's go to the second one. Figure 2.1 shows a cylinder containing gas compressed by the movement of a piston. Now here's the compressed gas, and here we have the final position of the piston. It can't go any further. Now here it was the initial position was here, and then we pushed it right to the end. Now initially the volume of the gas was 470 centimeters cubed. It means when it was here, the piston moves up and compresses the gas to a volume of 60 centimeters cubed, which is here. The whole arrangement is left for some time until the gas cools to its original temperature. The pressure now is 800 kilopascals. What was the initial pressure of the gas? So we go by this formula, P1V1 equals P2V2. Here our unknown is P1. So V1, which is the initial volume, which is here in green. The ones in green are the initial, the ones in yellow are the final. So the initial volume was 470. The final volume is 60, which is V2, and the final pressure, which is 800, and we left it in kilopascals. So eventually it will be 102 kilopascals. Now explain in terms of molecules the effect of on the pressure of the gas if it was not given time to cool to its original temperature. Now here the question told you that we left the arrangement for some time until the gas cools down. Now what if we didn't give it time to cool down? So the molecules will have more kinetic energy, which means it will move faster. So more collisions will happen with the walls of the cylinder, so the pressure will increase. So if we don't give it time to cool down, more collisions will happen and the pressure will increase. Now, the area of the piston is 5.5 times 10 to the power of -3 meters squared, which is written here as a decimal. Calculate the force exerted by the gas on the piston when the pressure is 800 kilopascals. Now here you have a pressure, you have an area, and you're asked for a force. So we go back to also a really simple concept, which is pressure equals force over area. In order to get the force, it is the pressure multiplied by the area. So we just multiplied the pressure, which is 800 kilopascals, multiplied by the area. So we will get 4,400 newtons, since newtons is the unit of force. Okay. Now let's go to question 7. Smoke particles. This is actually one of the important questions because it is related to Brownian motion. Now smoke particles are introduced into a glass box containing air. Light shines into the box so that when observed through a microscope, the smoke particles can be seen as bright points of light. Now, describe the motion of the smoke particles and account for this motion in terms of the air molecules. So here we have to talk also about the smoke particles and the air molecules. So here I divided this answer into 2 points. The first one is that for the smoke particles, they move randomly, as well as they have sudden changes of direction. They have a zigzag motion, and they appear or disappear from the view. They're like twinkling stars. They just twinkle, they pop and disappear. While for the air molecules, they collide with the smoke particles since they are larger. They are faster as well, and they are smaller than the smoke particles. So the smoke particles are larger than the air particles, so they also move randomly. Now, figure 5.1 shows quantity of a gas in a cylinder sealed by a piston that is free to move. So this piston is not fixed, you can move it. The temperature of the gas is increased. What will happen, if anything, to the piston? Now, since we increased the temperature, more collisions will happen. So they will push the piston to the right. It will move to the right. Now, what will happen to the pressure of the gas? It will remain constant. So here, since we increased the temperature, the volume increased, the pressure will stay the same. Okay? Now, the piston is now fixed. Now you can't change it. You can't move it. And the temperature is also increased further. Now, what will happen to the molecules and the pressure of the gas? Will it stay the same? No, it will increase because more frequent collisions will happen of the gas molecules with the piston. Now here, in order to get some sense of what's happening, so if you have a piston and it was free to move, and these two asterisks, they represent the variable that we increased or decreased. So here we increase the temperature. Since it is free to move, the temperature will rise, so the volume will rise because it's free to move. The volume will increase so that the pressure will stay the same. So the volume will increase in order to keep the pressure as it is. While if it is a fixed piston, as this case, you can't move it, and you increase the temperature, now the volume will stay the same because the piston is fixed. It can't move. The volume will, you can't, the volume will not increase. It will stay the same. So here, in order for the volume to stay the same, the pressure has to increase. Okay? So this is kind of what happens when you have a free to move piston or a fixed piston. Okay, now let's go to this one. Figure 6.1 shows a quantity of gas in a cylinder fitted with a piston P. Describe the motion of the molecules of the gas. Now, the molecules of the gas, they move in random directions, and then the gas molecules, they have random speeds as well. So they move very fast at very high speeds, and the molecules, then they collide with each other and with the walls, of course, of the container. Now, the piston is now slowly pushed down to decrease the volume of the gas. The temperature does not change. Now, since the temperature does not change and the volume is decreasing because we're pushing the piston down, so the pressure will increase because we decrease the volume. When the volume is reduced, more frequent collisions will happen between the molecules and the walls of the container or the cylinder. Before pushing the piston down, the pressure of the gas was 1 × 10⁵ pascals. Pushing the piston down reduces the volume from 500 centimeters cubed, so the green is also the initial, to 240, which is the final volume. We want the final pressure. So we go, as we did in the previous examples, P1 V1 equals P2 V2. Submit the values that you have. So you'll end up with a pressure of 2.1 × 10⁵ pascals. Okay, now let's go to this one. Here we have puddles of water form on a path after rainfall on a windy day, and this is important. In terms of molecules, state and explain how the rate of evaporation of the puddles is affected by the reduction of the wind speed. So if we reduce the wind speed, what will happen to the rate of evaporation? Will it increase? Will we have more evaporation or less? Now it will, of course, reduce the rate of evaporation, since we said that in evaporation you have molecules on the surface that have more kinetic energy. So if we reduce the wind speed, fewer evaporated molecules will be removed by the wind. So the rate of evaporation will be reduced. Now, if we increase the temperature, it will increase the rate of evaporation because we will be giving the molecules more energy, so they will move faster. So we will have more molecules that will have enough energy to escape the surface of the puddles. Now, figure 5.1 shows 2 puddles. We have a large one and we have a small one. State and explain how the rate of evaporation from the large compares to the one from the small. So how does it compare, like the rate of evaporation for the large puddle comparing to the small puddle? Now, it is greater, of course, in the larger puddle because it has a larger surface area, which means that more molecules will have enough energy to escape the surface. And as we said, that the evaporation only happens at the surface of the liquid, not like boiling. It happens throughout the whole liquid. Now let's go to the next one. A teacher shows a class examples of 3 states of matter. Now these are a solid metal block resting on the bench, a liquid in a glass beaker, and a gas in a clear balloon in the laboratory. Now figure 4.1a, this one, represents the arrangement of molecules in the solid. So here we have the arrangement of the molecules in the solid. These two are left blank. Now, complete the figure 4.1b and 4.1c to show the arrangement in both the liquid and the gas. Now, what you will have to do is that you have to draw the molecules of the liquid as random, and they have similar distances to each other, while you have to draw the ones with the gas also randomly, but they are further apart, and they have to be further apart. Now, in the list below, draw a ring around the state of matter that is easiest to compress, and of course, that is the gas. Now, why it is the easiest to compress? Because in gas molecules, we have more room for the molecules to compress, and also we don't have any repulsive forces between molecules, which will make the pressure on the walls of the container smaller, which will be easier, which will make the process of compressing the gas easier to do. Okay. Now, a small cylinder of compressed helium gas is used to inflate, to blow, or to inflate the balloons for a celebration. Now, in the box below, sketch a diagram to represent the arrangement of helium molecules in a balloon. So this is left blank, and you have to draw them. You have to draw them randomly positioned and widely spaced. Now, state and explain how the size of the attractive forces acting between the molecules of a gas compares to the size of the attractive forces between the molecules of a solid. So we're comparing the attractive forces in a gas with the attractive forces of a solid. Of course, the attractive forces between the molecules are much smaller between gas molecules than the ones with the solid molecules. So the attractive forces between molecules in a gas are much smaller than the ones in a solid, since of course that the gas molecules are much further apart. Now please pay attention to this one. This is very important. Now the helium in the cylinder has a volume of 6 times 10 to the power of -3 meter cubed, which is written also in decimal, and is at pressure of 2.75 times 10 to the power of 6 pascals. So this is in the cylinder. Now the pressure of helium in each balloon is 1.1 times 10 to the power of 5 pascal. And the volume of the helium in an inflated balloon is 3 times 10 to the power of -3. This is the amount of helium that we're putting inside this balloon at this pressure. The temperature does not change. Now, how many numbers of balloons that were inflated? Okay. Now, first of all, in order to get the number of the balloons, you have to divide the total volume of the helium over the volume of the helium in each balloon. Now, I have the volume of helium in each balloon, which is 1.1 times 10 to the power of, which is 3 times 10 to the power of -3 meter cubed, right? This is the volume of the helium in each balloon. Now, I want the total volume of helium. Is it really 6 times 10 to the power of -3? No. The 6 times 10 to the power of -3 is not the actual volume of the helium, because when the helium continues to leave the cylinder, now the pressure decreases. Now, at some point, the pressure will decrease until it is the same as the outside air, and the helium will not move no more. So it will not move anymore. So we will have some of the helium that remains inside the cylinder. And how much volume is that? It is the volume of the cylinder itself. In order to get this volume, which stays in the let's say in the cylinder, we have to use this P1 V1 equals P2 V2. So initially it was 2.75 times 10 to the power of 6 pascals multiplied by the original volume equals the pressure after the inflation, which is 1.1 times 10 to the power of 5, multiplied by this volume, which I don't know how much it is. So in order to know the real amount that came out, we subtract this volume minus the volume in each balloon. So this is the real amount that came out. So we divide this volume, the total volume, the real amount, over the volume of the helium in each balloon, which is 3 times 10 to the power of negative 3 meter cubed. So we will end up with 48 balloons. If you don't do this, you will get it wrong by 2 balloons. So you will not get the 48 balloons. So this is actually a question with a tricky idea that you have to pay attention to. Okay. Later, the temperature increases and some of the balloons burst. Now, why does this happen? And we see this all the time in birthdays and parties. Now, when you let's say when you put a balloon next to a lamp that emits heat, it will burst. Because basically, when you increase the temperature, the molecules, they move faster, so more frequent collisions will happen. So the molecules, they will hit the balloon surface harder, with a harder force, which rips the rubber, and so the balloon expands until it explodes. Okay, so this was also the second part of our videos. Now the third one will have the rest of the questions that are also related to thermal physics. So I hope you guys take care. Bye bye.